Hey everyone, welcome back. So today we are jumping headfirst into an intensive explainer designed as your ultimate A-level revision bootcamp. We're going to master some of the absolute trickiest P-block exam traps. If you've been, kind of struggling to connect the dots between atomic structure, physical properties, and chemical reactivity in Group 14 and Period 3, well, you are in the exact right place. We're going to lock in those high-level concepts right now.
Okay, here's our blueprint for the session. We'll be looking at periodicity and ionization enthalpy, comparing dioxide structures, group 4 chloride behaviors, and finally, lead and oxidation states. Let's just get straight to it.
Section 1. Periodicity and ionization enthalpy, foundational trends.
Okay, so take a look at this question. This right here is an absolute classic exam prompt simulator. It really tests your ability to connect physical, tangible properties to invisible atomic structure. When examiners ask you to explain a melting point trend across a period, they definitely aren't just looking for you to recite the numbers back to them, right? They want the structural why behind those numbers.
I mean, just wow, look at this dramatic drop. We go from the giant covalent network of silicon to the simple molecules of phosphorus, sulfur, and chlorine. Silicon is sitting way up there at over 1400 degrees Celsius. It requires massive thermal energy to break those incredibly strong three-dimensional covalent bonds. But as soon as we cross over to phosphorus, sulfur, and chlorine, the melting points just absolutely plummet. And why is that? Well, because you are no longer breaking covalent bonds to melt them. You're only overcoming much weaker intermolecular forces between simple molecules like P4, S8, and Cl2.
Now, while we're laying down foundations, nailing this exact definition is basically your ticket to full marks. Examiners expect highly precise terminology when you discuss energy changes. Missing the word gaseous or ground state? Yeah, that is a super easy way to drop a point you otherwise completely deserve. Don't let that happen.
So, the crucial point here is that while the trend generally decreases as electrons get farther from the nucleus, mostly because there's simply less attraction holding on to those outer electrons, tin and lead present a huge, classic trap for students. Actually, scratch that, it's not a perfect downward slope at all. Their ionization enthalpies are slightly off the expected trend. Why? Because tin and lead possess unexpectedly higher stability from filled and half-filled p orbitals. It literally requires a bit of extra oomph, extra energy to pull an electron away from that cozy, stable configuration. Do not let that little exception catch you off guard on test day.
Moving on to Section 2, comparing dioxide structures, the great structural showdown.
Examiners absolutely love testing this difference. Carbon and silicon are right next to each other in Group 14, and both react with two oxygens. Yet one is the invisible gas we breathe out, and the other is literally sand and solid quartz. I mean, just imagine if we walked around exhaling solid quartz. It's wild to think about. Let's look at the mechanics of why this happens.
Here is the perfect direct comparison you really need to visualize for your exams. Carbon dioxide exists as simple, discrete molecules locked together internally by double bonds, but there are only weak forces between the actual molecules. Silicon dioxide, however, that exists as a massive, continuous network of single covalent bonds in 3 dimensions.
The why behind all this structure is entirely about orbital overlap limitations. Carbon promotes a 2s electron into an empty 2p level to hybridize and form double bonds with oxygen. Because carbon is so tiny, its p orbitals can actually get close enough to overlap sideways, creating a super stable pi bond. Silicon atoms, however, are just significantly larger. This makes the silicon-oxygen bond physically longer. Because they're further apart, those p orbitals simply cannot overlap enough to form a stable pi bond. So silicon is basically forced into forming single bonds, bridging out to 4 neighboring oxygens in this massive 3D network. It's like a giant puzzle.
And the physical structure isn't the only thing that changes. As you move down Group 4, the dioxides transition from strictly acidic at the top, like carbon dioxide, which dissolves in water to form a weak acid, to amphoteric at the bottom. Memorize that word. This means oxides of elements like tin and lead can play both sides. They react with both acids and strong bases, like hot concentrated sodium hydroxide.
Section 3, Group 4 chloride behaviors, the breaking point.
Okay, what's really fascinating here is how lead-4 chloride physically cannot stay together at higher temperatures, unlike the elements at the top of the group. While carbon tetrachloride boils at 76 degrees and silicon tetrachloride at 57, look at the bottom row. Lead-4 chloride decomposes at 105 degrees Celsius. It doesn't just boil, it literally just falls apart. No way, right?
The reason for this ties perfectly back into atomic size. At the top, carbon and silicon form very stable, simple tetrahedral molecules. But as we go down the group, that central atom gets larger and larger. The bond between that atom and the chlorine gets longer. It's pretty simple. The longer the bond, the lower the bond energy. And lower bond energy translates directly into compounds that break apart much more easily, making reactions like hydrolysis significantly more vigorous as you descend the group.
And here is the visual proof. Seeing lead-4 chloride break down into lead-2 chloride and chlorine gas gives you exactly the equation you need to memorize. The heat actually forces it to drop its oxidation state.
Which brings us to section 4, lead and oxidation states, the flip instability.
Okay, if you only remember one thing from today, consider this graph your ultimate cheat sheet for the entire group's behavior. Just look at the two intersecting lines. The +4 oxidation state is highly favorable at the top with carbon, but its stability drastically, rapidly falls as you move down. Conversely, the +2 state is very unstable at the top, but its relative stability rises sharply as you reach tin and lead.
This phenomenon right here explains entirely why that lead-4 chloride from a moment ago spontaneously decomposed into lead-2 chloride. Lead strongly prefers the +2 oxidation state. It's all because of what we call the inert pair effect. Basically, the outermost s electrons become increasingly reluctant to participate in bonding as the atoms get heavier. They just want to sit there. By comparing these two tables, you can easily predict chemical behaviors without resorting to rote memorization. It's like a chemical seesaw. A stable lower state means the higher state is desperate to drop down, making it a strong oxidizing agent. A stable higher state means the lower state is desperate to gain bonds, making it a strong reducing agent. We can literally see that exact concept in action right here. Carbon monoxide, where carbon is stuck in a +2 state, absolutely wants to reach +4. Because it's so easily oxidized into carbon dioxide, it acts as an excellent reducing agent. It's so good, in fact, that it's used to reduce iron ore into iron in massive industrial furnaces. On the flip side, lead-4 oxide is desperate to reach its favored +2 state. It acts as such an incredibly powerful oxidizing agent that it can violently oxidize ice-cold hydrochloric acid straight into chlorine gas.
So let me leave you with a bit of a provocative question to chew on as you review your notes tonight. Extrapolating these trends is what truly secures an A grade. If the inert pair effect gets stronger and stronger the heavier we get, just imagine what happens at the extreme edge of the periodic table. Would a +4 state even exist down there? Mastering these patterns, truly understanding the why behind the orbital sizes, the bond lengths, and the relative stabilities, that is going to give you total, absolute confidence in your exams. Thanks for joining this intensive explainer session, and happy studying!